In this presentation, we will walk through a number of BACT examples for greenhouse gases. We will look at several different source categories. These examples are designed to demonstrate the kinds of technical and policy issues that can arise in a BACT review and how they can be addressed. These examples do not represent guidance on what an actual BACT review must address, and they do not represent any guidance on what constitutes BACT for similar sources that would undergo an actual determination. The first BACT example is for a municipal solid waste landfill. The BACT review for the landfill has two elements: the capture of the landfill gas, which contains a significant amount of methane, and also the control of the emissions of that gas. Now, there is a new source performance standard that's applicable to non-methane organic compound emissions from large municipal solid waste landfills. The NSPS addresses the capture and control of landfill gas. The NSPS is therefore a useful starting point for a greenhouse gas BACT determination, since it has detailed requirements for the design and operation of the gas collection system. Now, as far as this permit, example permit goes, the landfill size would indicate whether the NSPS actually does apply here. In this example, though, the applicant proposes to capture the gases consistent with the NSPS. For control of the gases, the NSPS has a number of options. In this example, the applicant is evaluating three of the options for treatment of the gas. This includes flaring, using it in an engine to generate electricity, and treating the gas for delivery to a natural gas pipeline. In this example, as part of step 1 of the BACT determination, the permitting authority asks the applicant to review two additional control measures: to, first of all, collect and control the landfill gas earlier in the life of the landfill than what would be specified under the NSPS. So the NSPS requires collection after a certain amount of waste is in place, and at that point there's an expected level of gas that's being generated and released. So the applicant is being asked to consider collecting and controlling the landfill gas earlier, prior to when the NSPS would require them to control that. Also, the applicant was asked to consider a gas turbine to generate power as opposed to the internal combustion engine, which the applicant proposed. At this stage, there are two options for gas capture: the NSPS compliant active capture system, and that same system with an earlier initiation of gas collection. So given this, there are now four options under step 1 that are considered available controls for this landfill gas. There were three proposed by the applicant and one that was added by the permitting authority. First of all, there's flaring, there's fueling engines to generate power, there's fueling a gas turbine to generate power, and then treatment and routing of the gas to a pipeline. In step 2, we would eliminate any technically infeasible options. In this example, the applicant demonstrated that the volume of gas would be inadequate to fuel a commercially available gas turbine. The permitting authority reviewed the record provided by the applicant and accepted the elimination of that option from further consideration. So now we're back down to three options, and we move on to step 3. And here we would evaluate the control measures or combinations of measures based on their control effectiveness. Now, the applicant used CO2e emissions over the life of the landfill as the effectiveness indicator. CO2e emissions reflect both the direct emissions of greenhouse gases and the additional CO2 produced to the extent that a gas would be combusted on site. The ranking analysis considered various combinations of capture systems and controls for overall effectiveness. Early capture of the gas and conversion of the gas to pipeline quality for export is the most effective combination from a PSD perspective. This would mean that the maximum amount of gas would be captured, and most of this gas would not be combusted on site, so that the added on-site CO2 emissions do not occur. Also, the flaring and the use of the engines were deemed to be very similar in their level of control. They both would reduce methane emissions significantly, and they would generate relatively small amounts of on-site CO2 emissions. Okay, in step 4, we would evaluate the most effective controls for their economic, energy, and environmental impacts. The analysis of the cost effectiveness was expressed as dollars per ton of CO2e reduced over the life of the landfill. And this was shown to have the primary approach to the economic impact. The applicant found the conversion of gas to pipeline quality was not cost effective. In addition, the applicant demonstrated that it would be more than double the overall cost of the project since the landfill was far from an existing pipeline. The NSPS compliant control system with early collection was cost effective for either the flare or the engines. The flare was more cost effective than the use of the engines because revenue from the sale of power from the use of the engines would not offset the added cost of the engines and a power transmission line. In addition, in step 4, the energy and environmental impacts are also considered. The application noted a positive environmental impact from the use of a flare because the NOx emissions for a flare would be lower than those for engines. Public comment identified positive environmental and energy and environmental off-site impacts arising from the use of landfill gas to generate electricity, which would displace off-site energy generation and the associated emissions from the generation of off-site power generation. The permitting authority determined that this benefit from the selection of the engines outweighed the lower NOx emissions and the better cost effectiveness of a flare. So in the step 5, the permitting authority selected BACT to be the NSPS compliant active collection system with earlier installation and operation, and also the landfill gas routed to engines and used as the fuel to generate electricity. The permitting authority then needed to determine the permit conditions that would make the BACT determination practically enforceable. Here they determined that the permit should include 4 conditions: a CO2e limit on the engine emissions expressed in pounds per kilowatt hour to be demonstrated in a stack test annually. Also, compliance with the landfill NSPS design, operating, and record-keeping requirements. Earlier trigger for gas capture and use, as we mentioned. And then finally, requirement to operate engines under a written operation and maintenance plan to assure combustion efficiency. Okay, now we'll move on to our next BACT example, which is a natural gas-fired boiler. In this next BACT example, it involves a modification at an existing source that is major for greenhouse gases. The applicant is installing a new 250 million BTU per hour natural gas-fired boiler. For step 1, we would again identify all available controls for this proposed source. In this case, we have oxygen trim control, an economizer, blow-down heat recovery, and also steam recovery. The permitting authority asked the applicant to expand the analysis to consider an air preheater, which is a heat exchanger which recovers heat in the exhaust to preheat combustion air. Accordingly, at this stage in the example, the permit applicant and the permitting authority agreed to include this, and so therefore we have 5 control measures that were considered available under step 1. In addition, public comment asked for consideration of a combined cycle natural gas-fired turbine. In response to that, the applicant explained that a boiler is necessary for 2 of the business purposes of the project. That would be providing processed steam, not electricity, and also meeting a varying steam demand, which the combined cycle system would not be able to do. The permitting authority agreed with the applicant's response in this case, and they rejected the combined cycle natural gas-fired turbine for consideration on grounds that it would redefine the source. Under step 2, here's where we would eliminate any technically infeasible options. In this example, however, the permitting authority determined that all 5 controls are technically feasible as demonstrated, and they're each is demonstrated and deemed to be available and applicable to this type of source. So then we go to step 3. In this case, we would obviously evaluate the remaining controls based on their control effectiveness. The applicant ranked control measures for the boiler based on their impact on thermal efficiency of the boiler after finding that the thermal efficiency was a useful indicator of CO2 control efficiency. So continuing still in step 3, the permit applicant completed a control effectiveness analysis with the following results. The most effective single measure is oxygen trim control. An air preheater is no more effective than an economizer in recovering the exhaust heat, and the applicant narrowed the review to the economizer only. The applicant next considered the effectiveness of combinations of control measures. They determined that the most effective combination of measures is the oxygen trim control, an economizer, the condensate recovery, and the blowdown heat recovery. This assessment was approved by the permitting authority. So then we would go to step 4, where we would evaluate the economic, energy, and environmental impacts of the most effective controls. The permit applicant completed the analysis of the cost effectiveness, and in doing so, the applicant considered both individual measures and the combinations of measures. The results were expressed as dollars per ton of CO2e reduced. And given the size and the layout of this facility, the boiler blowdown heat recovery was not determined to be cost effective. The next most effective combination of measures was the use of oxygen trim control plus the use of an economizer and the condensate recovery. So everything that we had on the most effective combination except for the boiler blowdown heat recovery. Any significant energy and environmental impacts are to be considered in this step as well. The application identified recovery and reuse of condensate as having a number of environmental benefits. One, it would reduce the use of feedwater treatment chemicals. It would also reduce generation of related waste, and it would reduce the amount of water going to the wastewater treatment at the site. This information provided additional support for the condensate recovery as part of the BACT determination. So the permitting authority determined, and the record showed, that the BACT was a combination of oxygen trim control, an economizer, and the condensate recovery. So as part of selecting BACT in step 5, the permitting authority needed to determine what permit conditions would be used to implement the BACT determination. And they concluded that there would be an emissions limit expressed in pounds per CO2e emissions per pound of steam produced. It would be implemented as a 30-day rolling monthly average. The CO2e emissions would be determined from measured natural gas use and the application of standard emission factors. Steam production would be determined from a gauge on the outlet of the boiler. In addition, there would be a requirement to install the boiler as described in the application as a design standard. Also, there would be a requirement to implement a preventive maintenance program for the air-to-fuel ratio controller on the boiler. And then finally, there would be a requirement for periodic calibration of the natural gas meter and the steam flow analyzer. Our next BACT example is for a petroleum refinery hydrogen plant addition. In this example, the applicant is proposing to expand the hydrogen capacity and hydrogen treating capacity of a existing major source refinery. For simplicity, this BACT analysis addresses the greenhouse gas BACT for the hydrogen plant that is being added in the context of a larger project. Here's a basic flow diagram for a hydrogen plant. Hydrogen will be produced via the steam methane reforming process. In this SMR process, methane and steam are reacted via a catalyst to produce hydrogen and CO. the reaction is endothermic, and the necessary heat is provided in a gas-fired reformer furnace. The reformer and the furnace are shown as a single box on this diagram. The carbon monoxide reacts further with steam to generate hydrogen and CO2 in the CO shift conversion. The hydrogen is then separated from CO2 and other impurities using a pressure swing adsorption unit. The permit applicant proposes to use the off gas from this step, which is shown here as the purge gas, as part of the fuel for the reformer furnace. This purge gas contains hydrogen, CO2, and other gases. Okay, so here's the description provided with the diagram that we just gave you. The conversion equations are also presented here. So as you see, through these two conversion processes, it yields 4 molecules of hydrogen and 1 of CO2 for every molecule of methane that is converted. So now we go into the BACT analysis. Step 1, identifying all available controls. The permit applicant listed the following control options for greenhouse gas emissions: furnace air-to-fuel control, the waste heat recovery, and carbon dioxide capture and storage. The permitting authority did not require the applicant to consider any additional control options beyond those in the application, and none were suggested in public comments. In step 2, this is where we would eliminate any technically infeasible control options. The permitting record shows that all 3 controls that were identified in step 1 are technically feasible because there is no evidence that any of these options are not demonstrated or not available and applicable to this type of source. Now we go to step 3 of the BACT review. The applicant ranked the control measures for the hydrogen plant based on the CO2e emissions per unit of hydrogen produced. The output-based indicator is a good way to capture the overall effect of multiple energy efficiency measures used in the design of a complex process such as a hydrogen plant. The permit applicant's effectiveness analysis included benchmarking data on the energy efficiency and the greenhouse gas emissions of recently installed hydrogen plants. Benchmarking data showed that this hydrogen plant would be a lower emitter on an output basis than similar new plants, and the permitting authority concurred with this determination. The applicant determined that the most effective control combination, without regard for cost, was one in which all 3 control options were included. That would be the furnace control, the heat recovery, and the CCS. So now we go to step 4, in which we evaluate the collateral impacts of each of the most effective controls. The applicant's analysis of the cost effectiveness of the measures and combinations of measures was expressed as dollars per ton of CO2e reduced. The applicant also determined the incremental cost effectiveness of adding measures to the mix. The information supplied by the applicant demonstrated that the transport and sequestration of carbon dioxide would not be cost effective because the nearest prospective location for sequestration was more than 500 miles away from the facility. Also, there was not an existing pipeline suitable for CO2 transport between the refinery and the sequestration location. The cost of transport was significant in comparison to the amount of CO2 to be sequestered and the cost of the overall project. In responding to public comments on the issue, the permitting authority noted that in circumstances in which a refinery was located near an oil field that used CO2 injection for enhanced recovery, the cost calculations for transport and sequestration would likely be in a range that would not exclude CCS on the basis of cost. Other significant energy and environmental impacts are also considered in this BACT Step 4. But in this case, none were presented in the application, and the only significant public comment on the issue was addressed by the permitting authority as noted above. Moving on to Step 5 of the BACT process, with the analysis and the record complete, the permitting authority determined that BACT was the combination of furnace combustion control and integrated waste heat recovery. The permitting authority determined that BACT would be enforced through the following set of permit conditions. There would be an emissions limit in pounds of CO2e emitted per pound of hydrogen produced, averaged over rolling 30-day periods. The CO2e emissions would be determined by metering the natural gas sent to the hydrogen plant. The hydrogen production would also be metered. And then finally, there would be a need to implement a program for calibration and maintenance of the meters and oxygen trim system. The greenhouse BACT example that we're going to cover next is for a coal-fired electric generating unit. Okay, in this example, the applicant is proposing to create a new greenfield subbituminous pulverized coal-fired boiler and steam turbine facility. And we will go through this individually. First of all, the BACT. Prior to getting to the BACT analysis, we'll just look at a diagram for this. Here's a diagram of such a facility. The coal is, in this case, pulverized and fed to the boiler. The steam is sent to a steam turbine to generate electricity. A number of efficiency measures, efficiency improvement measures are used in most of these designs, including use of an economizer, a steam reheater, an air preheater, the feed water heater, and the condensate recovery and reuse. Okay, so now we get into the BACT steps, and for step one, the applicant's BACT analysis contained essentially two measures. The first was to look at different efficiency measures for their boiler. One would be to consider the use of a supercritical boiler in turbine design. Now, supercritical design refers to the temperature and pressure of the steam that's going into the turbine. The higher the steam pressure and temperature, the higher the generating efficiency. Accordingly, the design of the turbine is optimized to the steam that it will receive. So they considered supercritical boiler and steam design. Also, they considered coal drying, which would enhance the combustion of the coal. Also, they considered optimized combustion with continuous control. In addition to the efficiency measures, they also considered a CO2 control through an add-on control technology known as carbon capture and sequestration. So in addition to what the applicant showed here, the state permitting authority requested that the BACT analysis also include ultra supercritical design, which would run at still higher temperatures and pressure and would result in a higher efficiency than the supercritical design. Also, integrated gasification combined cycle, or IGCC, and also motor efficiency improvements to increase the net output of the electricity and therefore reduce the fuel use. Here's a flow chart for the IGCC system. In this system, the coal is gasified, cleaned, and sent to a gas turbine which generates electricity. The heat in the turbine exhaust is then used to generate steam, which is fed to a steam turbine for additional power generation. Pre-combustion capture of CO2 is an option with coal gasification in the context of IGCC. In the gasifier, the coal decomposes in the presence of oxygen to create syngas, which is a mixture of H2, hydrogen gas, and carbon monoxide, along with other minor chemical compounds. To enable pre-combustion capture, the syngas is further processed to convert CO to CO2 while producing additional H2. The solvent absorption system can then be used to separate the CO2 from the H2. After removal of the CO2, the H2 can then be used as a fuel in the IGCC combustion turbine. Pre-combustion CO2 capture is less expensive than post-combustion CO2 capture. The advantages of this type of a system are the higher CO2 concentration and the lower volume of syngas to be handled in extracting the CO2. This would result in smaller equipment sizes and lower capital costs. During the public comment period, a commenter called for the use of natural gas instead of coal. While this happened to be after the BACT determination and the draft permit were out for comment, it relates to the control measures that were considered in Step 1 of the BACT analysis. The permitting agency determined that the use of natural gas instead of coal is outside the scope of BACT, and it represented a change in the basic design and business purpose of the facility. So in this case, the permitting authority decided not to include it as a Step 1 available control option. Okay, now we go on to Step 2. In the context of Step 2, all options are considered by the permitting authority to be available and technically feasible. So these include the ultra-supercritical boiler and the turbine design, the integrated gasification combined cycle, IGCC, coal drying, combustion control, variable speed motors, and carbon capture and sequestration. Now we go on to Step 3, where the controls are ranked based on their effectiveness. In this example, the applicant proposed to rank the measures based on emissions per unit of fuel used. Instead, the state required that the options be ranked by CO2 emissions on a net output basis, that is, the tons of CO2e per megawatt hour, so as to pick up the impact of the high-efficiency motors and the use of the fuel and the level of emissions associated with delivering power to the grid. It is determined that the most effective combination is either the ultra-supercritical boiler with a CCS or the IGCC with a CCS. Coal drying and high-efficiency motors were also included in both instances. Moving on to Step 4, in response to the agency's request, the applicant completes a cost analysis of CO2 capture, building and operating a CO2 pipeline, securing the rights to place the CO2 in the geologic reservoir, and operating the sequestration operation. The applicant argues that CCS would be beyond the scope of BACT due to the excessive cost in 3 bases. That is, the cost per ton of CO2 controlled, the cost of CCS as a percent of the project cost, and the impact of CCS costs and the economic viability of the project. After reviewing this analysis, CCS is dismissed by the permitting authority for both the IGCC and the ultra-supercritical designs based on excessive cost, siting issues, and parasitic electricity load. In the absence of CCS, IGCC was shown not to be superior to the ultra-supercritical design. Thus, in this case, supercritical was chosen as BACT as the most cost-effective with no adverse collateral impacts. All energy efficiency measures that were considered under BACT Step 1 were also required. The permitting agency documents the conclusion and has supporting documentation for the record. So here we have in Step 5, selecting the BACT. As I mentioned, the BACT included a ultra-supercritical boiler design with high-efficiency steam turbine, the control of the boiler-air-fuel ratio, the coal dryer using that low-grade waste heat, and the high-efficiency variable speed motors for the electric drives. And finally, the permitting authority determined that within the permit, they would have enforceable permit conditions for BACT that would be the annual limit in tons per CO2 per net megawatt hour, that would be on an output basis, using a rolling 12-month total of emissions and the megawatt hours to the grid. Also, they were to devise an operating and maintenance plan that would address the combustion controls, the steam turbine efficiency, and the operation of the electric motors. Our next BACT example will be for a cement plant. In this example, a new cement kiln is proposed. The product is finished cement for local markets. Cement is produced from raw materials such as limestone, chalk, shale, clay, and sands. They are quarried, crushed, ground, and blended to the correct chemical composition. The raw material is fed into a large cylindrical furnace called a rotary kiln, which rotates while the contents are heated to extremely high temperatures. The high temperature causes the raw materials to react and to form a hard nodular material called clinker. Clinker is cooled and ground with gypsum and other additives to produce Portland cement. CO2 is emitted from decomposition of the limestone and from the combustion of fuel in the kiln. So here's a process flow diagram for a cement kiln. The rotary kiln where the limestone is converted and the fuel is burned is in the center of this diagram, and this is also where the CO2 is generated. Thermal efficiency is boosted by recovering heat from the product in the clinker cooler, which is to the left of the kiln, and also by preheating the feed with kiln exhaust. A 4-stage preheater is to the right of the kiln in this diagram. For step 1, the process of identifying control options in this BACT analysis considered 4 different elements. First, the process technology or energy efficiency, fuel choice, product specification, and CO2 removal and storage. And we'll go through each of these in the next few slides. With regard to process technology / energy efficiency, the applicant proposed to use a preheater precalciner design which is more efficient than the older designs that have less heat recovery. The applicant presents the following features of the preheater precalciner design that improve thermal efficiency and reduce emissions of CO2 related to on-site fuel use. First, modern cement manufacturing facilities incorporate multi-stage preheaters prior to the kiln. A 5-stage preheater is proposed by the applicant. Note that the prior figure that was shown on these slides has a 4-stage preheater. A 5-stage preheater would provide greater heat transfer to the feed and better overall efficiency. Grate coolers are used to cool the clinker. The grate cooler is integral to the heat recovery from the clinker and higher thermal efficiency. A reciprocating grate cooler, which is the design with the greatest fuel use benefit, is proposed by the applicant. Also, a computerized automated control system is proposed to optimize the fuel combustion conditions. Two more energy efficiency measures are also proposed. Seals, kiln seals that are installed reduce heat loss. The applicant presents the information on the effectiveness and longevity of the seals and proposes a maintenance plan for the seals. Significant heat loss can occur through the kiln shell, and the proper installation of this keeps these losses to a minimum. The applicant presents the alternative refractory that were considered and demonstrates that the most effective refractory was chosen. The applicant presents data on the energy use per ton of clinker that has been achieved at recently built kilns as a demonstration that the proposed design constitutes BACT for the thermal efficiency aspect of the proposed kiln design. With regard to fuel choice, the applicant proposes to use a combination of coal as the primary fuel and also wood wastes when they are available. The applicant presents data showing that the other solid fuels, such as tires or waste plastics, do not represent a reduction in CO2 emissions at the kiln. The permitting authority agrees with the applicant. Another area for emission reductions is product composition. The applicant does not address product composition in the initial application. However, to the extent that one can make a finished product which meets all of the quality requirements with less clinker, the finished product will be less energy intensive and the emissions of CO2 per unit of product will be reduced. Fly ash from coal combustion can be used in a blended cement. However, the use of fly ash may be limited by byproduct quality requirements and fly ash characteristics. Given this, the permitting authority asks the applicant to consider maximum use of fly ash and other additives as blending materials with consideration of the markets to be served. The applicant presents the information on product specifications in the anticipated markets and indicates that up to 5% fly ash from a nearby coal-fired utility could be used in some of their product. A CO2 reduction in terms of CO2 per ton of finished cement due to fly ash is noted. This alternative is accepted for further review by the permitting authority. Finally, with regard to CO2 capture, removal, and storage, the applicant presents information on two means of capture and control: conventional carbon capture and storage, and the Calera process. The Calera process uses a wet scrubber to capture CO2 emissions and chemically convert the captured CO2 to carbonates. Carbonate minerals can then be precipitated from the solution, dried, and used to make blended cement or other building materials. Okay, now we go to step 2, which would be the step in which we would eliminate any technically infeasible options. During the public comment, the use of natural gas in place of coal is raised by a commenter. The applicant points out that it is technically feasible to use gas with a NOx increase. It would be with an increase in NOx emissions. However, there is no natural gas supply infrastructure with sufficient capacity in the area. The applicant shows that data demonstrate that the cost of getting gas delivered will not be cost effective. Therefore, the permitting authority reviews this and agrees that that this should not be considered under one of the available technologies. Regarding the technical feasibility of changing the product composition, the applicant presents data showing that the use of more fly ash will not allow them to meet product specifications. The applicant also presents data on the availability of other product blend materials showing that they can adversely affect product quality and there is no identifiable long-term supply. As a result, the assessment is limited to 5% fly ash and 80% of the product, averaged over 12 months. With regard to carbon capture and storage, the applicant points out that the Calera process is still under development and not commercially available. The applicant also notes that once it is commercial, issues of markets for the byproduct and cost would need to be considered. Lastly, the applicant points out that the nature of the Calera process and its products would be a change in their fundamental business purpose. The applicant notes that the capture and purification of CO2 from a cement kiln is under study and is not commercially available. The application indicates that CCS is not commercially available or technically feasible and should be dismissed. In this case, the permitting authority concurs. The next step is to evaluate the effectiveness of the remaining measures. The measures were ranked by the applicant based on CO2 emitted per ton of clinker. At the agency's request, the ranking was also done based on CO2 emitted per ton of finished cement. This change allowed the analysis to capture the impact that fly ash addition could have on emissions. In Step 4 of the BACT review, the economic, environmental, and energy impacts of the most effective controls are considered. The use of the high-efficiency kiln design and the use of the fly ash in the product were both found to be cost-effective on the basis of dollars per ton of CO2 eliminated. Other environmental issues were identified with efforts to commit to the use of alternative waste as fuels. However, alternative fuels have not shown a clear CO2 emissions reduction potential for the site emissions. In this example, BACT was determined to be the use of the preheater precalciner design with all of the efficiency improvements proposed by the applicant. Additionally, the applicant is to use 5% fly ash in the cement blend whenever the product specification allows for its use. The permitting authority set the following kinds of limits to enforce this BACT determination. The kiln is to meet a 365-day rolling annual average limit on tons of CO2 emitted per ton of clinker produced. For this purpose, CO2 emissions are determined with a continuous emissions monitoring system. A maintenance plan for the insulation and the kiln sills is also required. In operating and maintenance for the process optimization controls, including instrument calibration and maintenance, is also required. And finally, records of fly ash use in the product are required. If the annual average fly ash addition is less than 5%, the company needs to justify its lower use based on product quality concerns or client restrictions. Our next BACT example will look at a natural gas compressor station expansion project. In this example, the applicant is proposing to install 2 reciprocating compressors with reciprocating gas-fired engines at an existing natural gas pipeline compressor station. The applicant includes the following elements in the initial BACT determination. High-efficiency engine design to minimize combustion emissions. Air-to-fuel ratio control to minimize methane emissions from the reciprocating engines. Periodic inspection and maintenance of the compressor rod packing to determine when to replace the packing. Use of low-bleed, gas-driven pneumatic controllers to reduce methane venting. And installation of a new flare and periodic inspection and maintenance of that flare, which will handle natural gas emissions during upsets, malfunctions, and vented methane from the rod packing. So in the context of identifying all available controls for consideration, the permitting authority asks that the applicant consider a gas turbine with centrifugal compressor in place of these reciprocating engines. This is because the site already had a turbine, and the turbine will have lower greenhouse gas emissions than the engines would. Also, the permitting authority suggests that pneumatic controllers could be driven by instrument air instead of natural gas that would result in lower fugitive emissions of methane. During the public comment period, a commenter asked that that an electric drive be considered as an alternative to a fuel-based drive for the compressor. And lastly, the permitting authority asked that the applicant consider vapor recovery for methane control from the compressor rod packing. So at this point, there are 9 control options that are being considered, and they are listed here. The high efficiency engine design, the air-to-fuel ratio controller, the use of a combustion turbine instead of the engines, periodic inspection and maintenance of the compressor rod packing, use of low-bleed gas-driven pneumatic controllers, use of instrument air to drive the pneumatic controllers, use of a high-efficiency flare for upset emissions control, vapor recovery unit for the rod packing, and use of an electric drive instead of a gas drive for the compressor. So in step 2, the technical feasibility of these measures would be addressed. The applicant provides evidence that the electric service that does not exist in the vicinity of the compressor station, and that use of the electric drives, the vapor recovery unit, and the electric motor based on air compressors using off-site power generation will not be feasible. Further, the on-site power generation will not reduce the greenhouse gas emissions. The applicant also indicates that the site needs enhanced ability to handle load swings, and a turbine is not suitable for that purpose. So the permitting authority agrees that the electric drive, the vapor recovery unit, and the instrument air are not feasible, and also that a turbine drive will not meet the established project purpose. So now we go on to step 3, and the applicant ranks the measures and combinations of measures based on CO2e emitted per hour at full load. The most effective combination of these measures is the high-efficiency engine design, the air-to-fuel ratio control on the reciprocating engines, periodic inspection and maintenance of the compressor rod packing, use of low-bleed gas-driven pneumatic controllers, and the use of a high-efficiency flare for upset emissions control and venting the methane from the rod packing. So in step 4, this is where we would evaluate the collateral impacts. The applicant agrees to the most effective combination. There were no significant energy, economic, or environmental impacts that were identified by either the applicant, the agency, or the public through the public comment period. Therefore, BACT is determined to be those 6 measures that I mentioned earlier, and they are listed here. Lastly, the permitting authority needs to address the permit conditions that will be used to make the BACT provisions practically enforceable. The permit conditions include, for the engines, a monthly limit on the greenhouse gas emissions based on CO2e per horsepower hour, and this would include both for methane and CO2 emissions. Also, equipment requirements for the engine, air-to-fuel controls, the compressor rod packing, and the flare. Also, the development and implementation of a preventive maintenance plan for these control measures, including leak detection and repair. And finally, the installation of high-efficiency engines consistent with the representations in the initial application. Our next BACT example will examine a gas turbine electric generating facility. This example involves a proposal to construct a new 500 megawatt natural gas-fired combined cycle power plant with 2 combustion turbines, heat recovery steam generators with supplemental firing, and steam turbines. The natural gas will be fired in the combustion turbines. The combustion turbine exhaust is sent to the heat recovery steam generators. Those steam generators are typically configured with supplemental direct firing of fuel to allow for control and maximum output and efficiency. The steam will be fed into the steam turbines, and therefore the electricity will be generated from both the gas turbines and the steam turbines. In step 1 of the BACT analysis, the applicant identifies 2 measures for consideration: high thermal efficiency system design and carbon capture and storage. A public comment raises another control measure for consideration. The commenter calls for non-fossil fuel electricity generation. But the permitting authority, after reviewing the comment, determines that this is redefining the source and is therefore beyond the scope of their BACT review. In the review of the submittal, the permitting authority notes that benchmarking data for recent projects shows higher thermal efficiency than the proposed design. Therefore, the permitting authority asks for further consideration of alternative designs, including other turbines with higher efficiencies, as well as varying the ratio of gas turbine and steam turbine power generation at the facility. Under step 2 is where the feasibility is considered, and the applicant presents information indicating that CCS is not commercially available for gas turbine systems, and also that an appropriate sequestration site in the area is not demonstrated. In this case, the permitting authority reviews the evidence presented by the applicant and agrees that CCS is not technically feasible. In comparing the technologies in step 3, the applicant compares the options based on CO2e per megawatt hour. The analysis shows that an alternative gas turbine will provide higher overall efficiency. The analysis also shows that varying the steam-to-gas power generation ratio will not improve efficiency over the range of anticipated operating conditions. With a commitment to a higher efficiency gas turbine design and the dismissal of CCS as technically infeasible, no further analysis of cost and collateral impacts is done. Thus, we move on to step 5. The agency approved the higher efficiency design but had difficulty in trying to convert the high efficiency design to an emissions limit that would apply at all times and that would account for differing operating conditions, ambient conditions, and system degradation over its useful life. Thus, the permitting conditions were as follows: emission limits for CO2e based on a 30-day rolling total and an efficiency limit in BTU per kilowatt hour demonstrated in an annual compliance test.